All right, let's jump right into this explainer. Today, we're not just looking at a flat map. We're going on the ultimate vertical expedition, a journey to uncover the mind-blowing, complex system and structure of the very planet we call home. We're talking about the incredible processes happening miles above our heads and deep, deep beneath our feet.
Have you ever actually stopped to wonder what's truly inside our planet? Or, for that matter, where exactly space even begins? Just imagine you're climbing the absolute highest mountain, and you just keep going straight up into the sky. Or picture diving into the deepest, darkest ocean trench, and then digging even further down into the solid rock below. Well, today, we're going to explore exactly what you'd see and experience on that epic vertical journey.
Here's our roadmap for today's adventure. We'll start with the Earth's four spheres, then explore the atmosphere and ocean. After that, we'll journey to the Earth's core. Check out the dynamic rock cycle. Look at exogenic and endogenic processes. And finally, wrap up with geohazards, time, and resources.
Section 1. The Earth's four spheres. Let's kick things off by looking at the four perfectly balanced, interconnected systems that make life on Earth possible. You see, our planet isn't just some lifeless rock floating around in space. It's this beautiful, complex interaction of four distinct zones. First up, you have the atmosphere, which is the entire blanket of air covering the planet. Then there's the hydrosphere, the water zone. And this includes everything from the deep oceans and flowing rivers to trapped ice, underground aquifers, and even the water vapor in the air. Next is the biosphere, literally the life zone, hosting us humans, all the animals, plants, and microorganisms. And finally, the geosphere, which is the solid rock and soil zone we stand on. The crazy thing is these four spheres work completely in sync with one another.
Moving right along to Section 2, Exploring Atmosphere and Ocean.
So we can actually visually slice the sky and the sea into distinct layers. Let's start way up high. As we descend from the edge of space, about 480 kilometers up, we hit the exosphere. This is a super thin layer of light gases like helium and hydrogen, and it's actually where our communication satellites orbit. Dropping down from there, we enter the thermosphere, also known as the ionosphere. This is where charged particles react with Earth's magnetic field to create those stunning, colorful auroras, and it's also what reflects our radio waves. Next up is the mesosphere, basically our planetary shield, where burning meteorites get destroyed before they can hit us. Below that is the stratosphere. It's a nice, stable layer where commercial airplanes fly, and it houses the crucial ozone layer that absorbs harmful UV rays from the sun. And finally, we reach the troposphere, the bottom 13 kilometers. This is where clouds form, the wind blows, and where we actually live and breathe. Oh, and keep in mind, as you go higher up, both air pressure and temperature totally drop.
Now, plunging past land and straight into the hydrosphere, we can stratify the ocean based on how much light it gets. We start in the sunlit surface zone. It's shallow enough for light to easily penetrate, making it perfect for plants to thrive. But as we dive deeper, that light fades into the twilight zone. It's pretty tough for plants down here, but it's the absolute perfect hangout for massive marine animals. Think giant squids and various whale species. Finally, we drop into the pitch-black dark zone. It is incredibly deep and absolutely no sunlight reaches it. None. So to survive down here, most animals have developed these bizarre shimmering bodies, or even the unbelievable ability to literally glow in the dark.
Up next, Section 3, Journey to Earth's Core.
Okay, let's leave the ocean floor behind and dig straight down into the geosphere to uncover the hidden structure of the Earth itself. Starting right at the top, we have the crust. This is the outermost solid rock layer we stand on, mostly made of lighter elements like silica and oxygen. Just beneath that is the thickest layer of all, the mantle. Now, the very top of the mantle paired with the crust makes up the solid lithosphere. Go a bit deeper and you hit the asthenosphere, which is a semi-liquid layer of magma where convection currents are constantly flowing, followed by the lower solid mesosphere. If we keep digging, and I mean really digging, we finally hit the core. The outer core is this incredibly hot, swirling liquid layer of iron and nickel, and right at the dead center of it all is the inner core.
Now, here is the really mind-blowing part. At the very center of that inner core, even though it's made of solid iron and nickel, the temperature reaches a staggering 6,000 degrees Celsius. Just to put that into perspective for you, that is literally as hot as the surface of the sun. The immense pressure down there actually keeps the metal solid, despite that terrifying amount of heat.
All right, on to Section 4, the dynamic rock cycle.
Riding that intense heat from the core all the way back up to the crust, we find three main types of rock, and each one has its own unique origin story.
First up, we've got igneous rocks. These guys are literally born from fire. They form when magma or lava flows out of the mantle, cools down, and freezes, locking in all sorts of minerals. Then, we have sedimentary rocks. These are built from tiny fragments carried by rivers, wind, and glaciers that settle and get heavily compressed over time. Because they're deposited in layers, they're often hollow, and get this, they are the only rocks that contain fossils. Finally, there are metamorphic rocks. These are actually just igneous or sedimentary rocks that got shoved deep underground and subjected to such intense heat and pressure that they chemically changed. They become the absolute hardest, most crystalline rocks out there, like marble.
And the wildest part is, these rocks are all connected in this continuous, never-ending recycling program. Over thousands of years, magma can erupt and cool into an igneous rock. Then that rock gets weathered and eroded by rain and wind into tiny little fragments. Those fragments are transported, settle down, and get compressed into layered sedimentary rock. If those layers happen to get pushed deep underground, extreme heat and pressure literally bake them into super tough metamorphic rock. Push them even deeper, they melt right back into magma, and the whole shebang starts all over again.
Which brings us to Section 5, exogenic and endogenic processes. So you might be wondering, what massive forces are actually driving this whole rock cycle, shaping our mountains, carving our valleys, and literally moving entire continents? Well, we categorize these giant planet-shaping forces into two types, exogenic and endogenic. Exogenic processes happen right out on the Earth's surface, driven by outside energy, mostly from the sun and gravity. This includes things like weathering, where temperature changes and rainwater break down rocks, erosion by wind and ocean waves, and mass depletion, like landslides. On the flip side, endogenic processes are caused by immense forces deep within the Earth. That intense heat we talked about from the core and mantle creates convection currents in the asthenosphere. And those currents, they drive plate tectonics, constantly moving the Earth's crust, causing continents to drift and crash into each other, and fueling the magma activity that creates erupting volcanoes.
Finally, let's look at Section 6, geohazards, time, and resources.
Now, when these incredibly powerful endogenic and exogenic processes interact with human environments, they can create highly dangerous phenomena that we absolutely have to monitor. We call these natural disasters geohazards. Simply put, a geohazard is an extreme geological process that leads to widespread damage, destruction of property, and, sadly, loss of life. Endogenic forces trigger terrifying large-scale events like earthquakes, volcanism, and tsunamis. Meanwhile, exogenic forces can lead to massive landslides and sudden sinkholes. We even have localized geohazards to worry about, like quicksand in wetlands and acid rain, which is actually heavily influenced by human industrial pollution. It's a stark reminder of just how dynamic and unpredictable our planet's surface can really be.
Thankfully, we're not totally flying blind here. Advances in science and technology provide absolutely crucial early warnings to help us prepare for these disasters and save lives. For example, scientists have invented incredibly sensitive seismographs that can detect even the slightest vibrations of an earthquake. They've also placed high-tech radars all along vulnerable shorelines that use satellite connections to ping early tsunami warnings. They even placed these super cool acoustic sensors inside gravel backfills on hillsides. Basically, if the slope even begins to deform, the shifting gravel generates acoustic emissions, instantly triggering an alarm for a potential landslide.
By studying all of these processes, we actually learn a lot about time and our natural resources. Take water, for instance. The constant evaporation and condensation of the water cycle means that the total amount of water on Earth is always constant. It never changes. Meanwhile, those fossils trapped in the layered sedimentary rocks we talked about act like a giant geological timescale. They literally let us determine the age of the Earth and track how life has evolved over millions of years. But here's the catch. While our total water supply is constant, our access to clean, usable water is incredibly fragile. Surface water in our rivers can be easily ruined by industrial waste, and our precious underground water is at severe risk from chemical fertilizers and pesticides leaching down from agriculture.
We've journeyed all the way from the edge of space down to the boiling core and back up again. We've seen firsthand how the atmosphere, the water, all living things, and the rocks themselves are so deeply, intricately interconnected. So I want to leave you with this final thought. Knowing that our resources are limited and seeing how vulnerable they are to human activity, what steps will you take today to help preserve this incredibly complex, absolutely beautiful system we call Earth? Really think about it.